Hello everyone, my name is Shayan Islami and I'm presenting with the title of New Technological Solution for Friction Stir Welding of Composites. Friction stir welding is based on frictional heat between the rotating tool and the base material under an axial force. The welding tool plays the most important role in this process, followed by axial force and welding temperature, which is a result of axial force welding tool and the welding parameters, and after all this process can be optimized. This slide shows welding tool design development for welding polymeric material, which I studied during my PhD, starting in conventional welding tool to a stationary shoulder till the final tool design. Different geometries and material were tested. This is the final tool design for welding polymeric material. The tool made of a stationary shoulder out of PIC and with a large copper sleeve equipped with a thermocouple shaft to monitor welding temperature. This tool could obtain weld up to 97% of parent material tensile strength. However, in order to study the behavior of composite material during frictional stir welding, three different tool designs was tested for joining thermoplastic composite in the butt joint configuration. The first tool is a normal conventional tool that is used for welding metallic material. The second is the PIC stationary shoulder, which we developed for welding polymeric material, and the third is called hybrid tool, which is combination of a stationary and rotating tool. For this study, polyamide 6 reinforced with 30% short glass fibers was chosen to weld in a butt joint configuration, and we studied different tool design geometry and their effects on the weld quality. The weld direction was perpendicular to the fiber direction, as you can see in the picture. On the right top picture you can see the final setup for welding, and on the bottom the specimen geometry for mechanical characterization. As the axial force play a fundamental role in this process, the clamping device equipped with load cells was developed, and with this device we could monitor axial force in three different directions: Fx, Fy, Fz, as long as holding the parent material rigidly during the welding process. It was concluded that the traverse and rotational speeds have the main effect on the traversing and lateral forces during the welding. Also, it was possible to distinguish defect formation that are not detectable using visual inspection, as you can see in the right image, and this step created in the axial force was related to the formation of the gap during the welding. Also, using a developed tool, which is a stationary tool, the axial force is almost constant during the welding. And as you can see here, the difference between the stationary shoulder tool and rotatory shoe regarding the axial force. This is the final setup for FSW. At A you can see the 3-axis CNC machine, B tool design, C the clamping device, sensitized clamping device and data acquisition system. At D thermographic camera, E and tools thermocouple shaft for recording the welding temperature. This slide shows the surface quality of the welded plates using the three different tool concepts. As you can see, the conventional tool had a very rough surface quality compared to the PIC stationary shoulder. The PIC stationary shoulder had the smoothest surface, and for the hybrid tool the surface was rough, but not as rough as the conventional tool. The conventional tool create the poor surface quality, also the tunnel defect on the middle of the weld. In general, it was concluded that conventional tool, which is rotating shoulder, is not suitable for welding composites as well as polymers due to the flash defects and bad surface quality on the weld area. So a stationary shoulder is required to forge the plasticized material into the weld.
The next tool that was tested was the PIC stationary shoulder that was developed for welding polymeric material. The Taguchi table was conducted for optimization process for 3 parameters, each in 2 levels: rotational speed, welding speed, and axial force. 5 specimens was produced for each combination and was tested to study the effect of the welding parameters on the joint strengths. Ultimate tensile strength of the welded specimen is shown in this table. As you can see, the best weld achieved maximum rotational speed, also maximum welding speed. However, the welding speed has higher contribution regarding the influence on the weld strength, followed by rotational speed and axial force. However, you have to keep in mind that all the welding parameters are related to the specific tool design. Also, the welding temperature is shown, and it's clear that the strength of the produced welds are increasing as the tool is advancing due to the increase of the welding temperature. And low thermal conductivity of the PIC preserves its generated heat inside the copper sleeve. Also, as you can see in the picture on the right bottom, PIC stationary shoulder creates a smooth surface by forging material inside the steer zone. However, with this tool design, maximum joint efficiency of 43% was achieved when compared to the base material. And in this slide, the comparison between the parent material and welded specimen is shown. As you can see on the left, the tensile strength of the parent material in the both direction, which is parallel to the fiber direction and perpendicular to the fiber direction, and the maximum joint efficiency of 43% obtained for the S4 specimen, and the welding speed with 57% contribution had the highest contribution, followed by rotational speed for 12% and axial force with.
An innovative welding tool was developed and tested. This tool is a combination of a rotating shoulder with a stationary shoulder. The purpose for that was to compensate lack of the frictional heat when using a stationary shoulder, because rotating shoulder has the main effect on generating frictional heat, and with the absence of a rotating shoulder, the welding tool suffers from lack of heat generation. And the stationary shoulder around would forge the plasticized material inside the weld bit, and the probe would steer the plasticized material under an axial force. However, due to the size of the H13 welding tool and capacity of the available machine, it takes time just for the tool to heat up to the desired temperature during the dualing stage. So in some cases, additional heat source was needed. Also, this tool demands high torque as the contact area between the tool stand and copper sleeve were increased significantly in order to compensate lack of the generated heat when is compared to the PIC tool. The welding parameter range that could be tested with this tool and the available machine was very narrow, as a spindle was unable to apply enough torque. In this slide you can see the visual inspection of the welded plate using the hybrid tool. The different marking of the welded plate is shown. For example, the stationary shoulder effect, as you can see, also the rotating shoulder effect and the probe effect. The surface quality was poor compared to the PIC stationary shoulder, but this can be solved by coating the stationary shoulder. As you can see on the temperature and time graph, the temperature was much more stable using this tool due to being a steel material, and also on the right you can see the actual forces during the welding. Despite the fact that the surface quality was poor when compared to the PIC tool, the strength of the welded specimen was higher. As I mentioned before, the range of the parameter that could be tested using the available tool and the machine was narrow. However, we could manage to use those parameters for testing and welding the plates, but we preheated the tool up to 200 degrees instead of dwelling for a long time. Also kept actual force at 600 Newton, RPM 2000 and welding speed of 20 millimeter per minute. You can see the 5 specimens that was produced and tested, and all of them broke at retreating side of the weld. In general, this tool showed a promising result, and following improvement is required for further investigation. First is the maximum probe penetration to eliminate the root defect, because as you can see on the right side, the probe could be longer to eliminate the root defect at the bottom of the weld. Also ceramic coating of the stationary shoulder for better surface quality, and also heat isolation of the copper sleeve to localize the frictional heat and don't lose the heat for heating up the steel part, and we just have to be focused on the copper sleeve, and that can be by isolating the heat. Also better machine or increase the spindle capacity to generate more torque is required to use this tool. Parallel to frictional stir welding and the development that I mentioned, we are developing and patenting a new joining process, which is combination of frictional stir spot welding and riveting process. With this concept, a rotating tool will hold a filler material which is consumable, and the same material could be same or different than the base material. However, those filler would steer the base material and mold the rivet on the two sides. As you can see on the right side, that is the actual joint specimen, and on the bottom is the X-ray of the joint area. This was a 20% short carbon fiber, and it was 3D printed, and as you can see, as a printing is a defective process, you can see all the layers of the printing, and in the middle of the joining area that filler enhance the mechanical properties of the material, and this method can be used for joining polymers and thermoplastic based materials. And for the conclusion, the welding tool is the most important factor affecting weld quality and appearance. It was concluded that conventional tool is not suitable for welding thermoplastic based composite, and use of the high performing thermoplastic for a stationary shoulder such as PIC or PAI creates sound surface quality. Also, a slip size and geometry have a strong effect on the heat generation. The maximum joint efficiency was 58.8% of the parent material's tensile strengths, and this was achieved using the hybrid tool. After the tool design, rotational speed and the welding speed has the main effect on the weld quality. Axial force is responsible for forging pressure and heat generation, and the developed device enabled to use the axial force as a welding parameter even using position control welding. The welding speed and the rotational speed have the main effect on the traversing and lateral forces. The developed sensitized clamping device can be used for health monitoring of the welding process. Also, the applied force is kept constant during the operation using a stationary shoulder tool. Parameter optimization is a crucial factor to obtain optimum weld temperature and quality, and dwell time is responsible for heating the tool before advancing, but for using the hybrid tool, preheating the tool was required. The weld temperature can be controlled with rotational speed, welding speed, and axial force, and the welding parameter should be optimized for each individual welding tool. Thank you for your attention.